Hello students, welcome to my second lecture on signals and systems. In the previous lecture, we have studied the first part of the module 1, Introduction to Signals and Systems. Today, we will study the second part. So previously, we finished our lecture with advantages of analog and digital systems. So let's continue from that, okay? So as we can see from our last lecture that both analog and digital lectures have its pros and cons, and we need both of them time to time. So converting them from one form to another is necessary. Telecommunication is one sector where we need their frequent conversion. For this conversion, we need analog to digital and digital to analog converters. For converting from analog to digital, there is a limitation for lower limit of the sampling rate. Now what is this sampling rate? In previous lecture we are talking about an example of going from Kolkata to Darjeeling and calling another person to give your location every 15 minutes. So what the other person was doing was taking samples of path of your journey every 15 minutes, that is 900 seconds. So sampling rate of path of your journey was 1 by 900 Hz. Now there is a limit of how slow this sampling can be done. And if we take example at a lower frequency than that, we would not be able to reconstruct the original signal. And that is our goal here, to reconstruct the original analog signal as precisely as we can. So why do we need to reconstruct the analog signal? Suppose you are talking to your friend via mobile phone. So actually what is happening there is that your analog input, that is your voice, is getting sampled by your phone at a very high frequency and being converted to digital signal. After sampling, your voice signal is getting converted to digital signal. Now with the help of antenna in your phone, it is getting transmitted to your nearest phone tower, and that tower is amplifying the signal and sending it to another tower. In this way, via your friend's mobile antenna, that signal reach your friend's mobile phone. Now your friend's phone is converting that transmitted signal, which is digital in nature, to analog signal and reconstructing what you said via your mobile phone. So now we can see the necessity of reconstructing the original signal. Mobile phones use analog to digital and digital to analog converters to achieve their task. So that was an example of analog to digital and digital to analog converter. Okay. So now back to the lower limit of the sampling frequency. Now to reconstruct the original signal, there is a lower limit of the sampling frequency which is mentioned in the theorem called Nyquist sampling theorem. If you put it simply, according to this theorem, if the frequency of your voice is say 1 kHz, the sampling of the signals need to be done with a frequency with at least 2 kHz or more than that. If we sample your voice signal at say 1.5 kHz, we can transmit the signal to your friend, but he won't be able to understand anything at all because your full speech would not be reconstructed at your friend's end. The detailed definition is mentioned here, that is an organized purposeful structure that consists of interrelated and interdependent elements. These elements continually influence one another, directly or indirectly, to maintain their activity and to achieve the goal of the system. But to put it simply, a system is a purposeful structure that work together to achieve a common task. Now, here are some examples of systems. A circuit involving any of the elements like capacitor, inductor, resistors, etc., or permutation combination of any of them can be considered as system. A communication system is another example. The very device that you are using right now to watch this lecture, be it laptop, desktop, mobile or tablet, is an example of a system. Human body itself is another example of system that consists of several subsystems. Different organ systems work together to achieve a common task. The university that you are studying in is an example of a system. It has different departments that work together to attain a task. Our Indian government is another example of system. It has legislative, executive, judiciary subsystems which run the government to attain a single goal, to run the country according to the Indian constitution. But for now, we are only interested in electrical systems and how they behave for different inputs. So periodic signals. Signals that repeat them after a fixed time are called periodic. Both continuous and discrete time signals can be periodic. X of t, a continuous time signal, is periodic if and only if x of t is equal to x of t plus t0 for any t and any integer n. That means after t times it repeats itself. Okay. Here are some examples of periodic signals. Graph of sin x. The top one here is periodic in nature. The bottom one is graph of cosine. It is also periodic. Tangent waveform on the top or secant waveform on the bottom. All these functions repeat themselves after 2 pi radian or 360 degrees. But that doesn't mean that time period can only be 2 pi. It can be any finite value. It can be 2, 20, 3, 19.3, 16.667, 15.44, etc. Anything, but it must be finite, because from common sense we can understand that anything that repeats itself after infinite time is not repeating at all. Okay. For non-periodic signals, x of t, a continuous time signal, is non-periodic signal if x of t is not equal to x of t plus t0 for any t and any integer n. To put it simply, it does not repeat itself after any amount of time. An exponential function, which you can see on the right side of the slide, is an example of non-periodic signal. Now for discrete type signal to be periodic, there is a similar condition. A discrete time signal is periodic if x of small n is equal to x of small n plus capital N. And for satisfying the above condition, the frequency of the discrete time signal should be ratio of two integers. Let's understand that in depth. So first we have to determine value of omega from equation by comparing it with the standard discrete form of the equation. Then divide that omega with 2 pi, and the resultant value must be an rational number for the signal to be periodic in nature. So what is a rational number? In mathematics, a rational number is a number that can be expressed as fraction p by q of two integers, a numerator p and a non-zero denominator q. Since q may be equal to 1, every integer is a rational number. So 2 by 3, 5 by 9, 9 by 5, 9 by 1 are all rational number, but pi is not rational number. Any value involving pi is not rational number either. Though in lower classes we have learned that pi is equal to 22 by 7, but it is actually the nearest approximation of the actual value of pi. So any answer involving pi in it is not rational number. So in this way we can determine if the given discrete signal is periodic or not. To summarize, periodic and non-periodic signals in continuous time signal and discrete time signal. In continuous time signal, we have to look for capital T. After capital T time period, the continuous time signal repeats itself. In discrete time signal, we have to look for n. After n time period, the discrete signal repeats itself, and omega by 2 of the signal must be rational. Now, as we are able to differentiate periodic signals from non-periodic, let's add two periodic signals with two different periods. Now, what will happen? Two things. First, the resultant signal can either be periodic, or second, the resultant signal can be non-periodic. For the first case, we need to determine what will be the time period for the resultant periodic signal. It can be seen from the example problem here that first we have to determine time period of each signal, then find the minimum value of the ratio of these two numbers In this, 6 by 8 can be reduced to 3 by 4. Now multiplying 4 with 6, we get 24. We could have multiplied 3 with 8 as well. Now this 24 is the time period of the new resultant signal, which we got by adding two periodic signals. Now how would we determine whether the addition of two signals will be periodic or not? For that we need to determine whether capital T1 by 2T2 is rational or irrational. If it is rational, then the resultant is periodic. If the resultant is non-rational, then the resultant signal is non-periodic. Signals that is predictable in nature and can be expressed mathematically are called deterministic signal. In short, we know the value of these signals at any given time. For example, x of t is equal to sine 3t is deterministic signal. On the other hand, signal that is unpredictable in nature, whose values are random, are called non-deterministic signal. Any type of noise, whether it is thermal, electrical, is an example of non-deterministic signal. Okay, so thank you everyone. Goodbye.